Hello everyone. Today we are here to discuss full state feedback control for a bus suspension. We will be discussing some history, background information, the modeling process, and experimental results for this study. The following presentation is brought to you by Jacob Wirt, Jason Lehrer, and Josh Hawk at Penn State Berks campus. As previously stated, we will be providing a brief history and background information on suspensions. Throughout history, there have been several different types of suspensions that ultimately led to the technology we have today. One of the first suspension systems created was a strap suspension. This was used on ox-drawn carts that had the carriage swing on iron chains attached to the wheeled frame. Although no modern vehicles use this suspension, it remained the basis for all suspension systems until the turn of the 19th century. Next, we have the leaf spring-based suspension. This was a simple form of spring that was commonly used for vehicles. Leaf springs were originally called a laminated or carriage spring, and even sometimes referred to as a semi-elliptical spring. As shown on the picture, this form of suspension consists of a slender arc-shaped piece of metal cut to rectangular cross-sections. This form of suspension is known to have dated back to the medieval times. Lastly, we have spring and damper suspension systems. The way these two components interact make for a perfect means of reducing oscillations transferred to the passengers. The springs are used to deflect the vehicle as it goes over a bump or pothole. Considering the spring would just bounce up and down, the dampers or shock absorbers are used to dissipate energy away by the use of an oil-filled cylinder. Next, we have some typical requirements for an efficient suspension system. The suspension must both support the handling of the vehicle while providing ride quality. Unfortunately, these two goals are at odds with one another. The tuning of suspensions involves finding the right compromise. When perfectly tuned, the suspension will not only reduce oscillations, but also make these oscillations settle quickly.
There are several parameters that we will be using to model this system. The body mass, which we are representing as M1, which will be a quarter of an unloaded bus, and that's going to be approximately 2,500 kilograms. The suspension mass, which is 320 kilograms, the spring constant of the suspension system, the spring constant of the wheel and tire, the dampening constant of the suspension system, and the dampening constant of the wheel and tire. We have a control force U, which, when acted on the system, will limit the max overshoot to less than 5% and the settling time to less than 5 seconds. We will first observe the effect of the system without the controller force U being implemented, and then we will see how it acts when it is implemented.
A general transfer function was created for the system without the controller. Using the parameters specified in the earlier slide, a step response was created using a step of 1. The graph shows a max overshoot well above 5%, and the settling time is well beyond the desired time of 5 seconds.
This system was modeled using Simulink. The first step is to model the integrals of the accelerations of the two masses. With A1 and A2 as the acceleration input line, we can place two integral blocks with output lines connected between them to determine the velocities and the positions of the two masses. Using gain blocks, we can represent the two masses. One gain block is set to 1 over m1, while another is set to 1 over m2. Two summation blocks, sum1 and sum2, will be used to sum the forces acting on the masses. For this system, there will be 3 forces acting on the body mass, sum 1, and 5 total forces acting on the suspension mass, sum 2. The body mass experiences forces from spring 1, damper 1, and a controller force in 1, which is initially set to a step of 1. The suspension mass will experience forces from both springs, both dampers, as well as the controller force. The force that spring 1 applies is equal to the spring constant times the difference between position 1 and x1. We can use a summation block to take the difference between the two positions and then attach it to the gain block, which is equal to the spring constant. This force is then attached to the appropriate terminals on the summation blocks, negative on sum 1 and positive on sum 2. The force from damper 1 is equal to the dampening coefficient times the difference between the two velocities. We will use another summation block to take the difference between the velocities and a gain block to represent the dampening coefficient. This dampening force is attached to the negative terminal on sum 1 and the positive terminal on sum 2. The second spring and second dampening forces are both dependent on the ground profile W, velocity 2 and position 2. These forces are acting solely on the suspension mass and will be positive forces inputted into sum 2. The controller force in 1 acts between the two masses and is attached to both sums. A linear model of the system is extracted from the Simulink model and put into MATLAB by using in1 and out1 blocks and the MATLAB function linmod. We will extract the output of the two positions with the out1 block. Using MATLAB, we can model the system when a step input is applied. This graph shows the output response of the system. Recall that we desired a settling time of less than 5 seconds and a max overshoot of less than 5%. We can see that this system obviously does not meet this desired criterion. The next step is to implement the full state feedback control. Before we can do this, we need to make some changes to our model. We need to generate several state outputs. These include the difference of the velocities, the position of x1, the velocity of v1, the input step w, and the controller force. This system is now copied into a subsystem which outputs the 5 scalar state variables previously mentioned. Using the MUX block, these scalar outputs are combined into a vector signal. The output of the MUX block then goes through a gain block which contains our matrix for the feedback gain. These gain values were found primarily through trial and error. Using this gain and negative feedback loop, we can see that on the graphs that the max overshoot and settling time meet the criterion that was previously mentioned.
This is the response for the system for the unloaded bus weight with the addition of the controller. The controller was able to reduce the max overshoot to below 5% and the settling time to less than 5 seconds. In order to determine if the controller would be efficient for the system, additional tests needed to be done. An additional test was done assuming that the bus would be loaded. The assumption is that the bus would have a mass of 3,402 kilograms, which would assume that the bus would have a moderate amount of people on it. The results of the response can be seen on the graph compared to the unloaded bus. As you can see, the controller was able to manage the response of the loaded bus, limiting the overshoot to fewer than 5% and decreasing the settling time to less than 5 seconds. A second test was done increasing the weight to 4,650 kilograms, which would assume the bus would be at maximum capacity. The results of the response were also graphed compared to the unloaded bus. Like the previous case, the controller was able to manage the system to meet the requirements. Now this brings us to our conclusions. The system's original response without the controller was not optimal. The max overshoot and the settling time were well above the desired values of 5% and 5 seconds. In order to improve the system's response, a controller was used. Adding the controller helped to reduce the max overshoot and decrease the settling time below 5 seconds for the initial mass of 2,500 kilograms, which was assumed to be an unloaded bus. To determine if the controller was efficient for the system, 2 additional tests were done assuming the bus was loaded. The first additional test assumed the bus was loaded with a moderate amount of people, increasing the mass to 3,402 kilograms. The controller was still able to be successful in managing the response with an overshoot of less than 5% and a settling time less than 5 seconds. The second additional test assumed the bus was at maximum capacity of 4,650 kilograms, and the results were the same as the previous test. This concludes that the addition of the controller is effective for the system modeling a bus's suspension.